back where we were at. And I actually had posted a lesson on Friday, and I want to just quickly, I don't want to spend much time on it, because if you haven't watched it, you can go back and watch it. But it was on that KPKC. And when we have, if you look on the chapter 13 quiz, and I'm going to point it out. So those of you that are in class, you can look. And tomorrow I will give it to those that will be here tomorrow. Lorik, are the notes coming up?
Yeah, they're up. Oh, yes.
They are? Okay. So let me go back. I was a little bit ahead. So where we left off on Thursday was we left off here with this KPKC. So, whoops, we got it on the computer. We don't have it on here. But quick review of this chapter. Okay, so we said this chapter is on equilibrium. Okay, so we talked about, well, what does that mean? And we said equilibrium is where we did the double arrow. And we talked about the reaction going left to right, as we've talked about all year long for a year and 3/4. But what happens too is the reaction goes backwards. It goes, the products react and they make the reactants. And so we talked about equilibrium, the double arrow thing. And some reactants go way to the right, some reactions go way to the right, some go to the left. And then we had this kind of an unusual, almost quirky thing. But if we take this thing called the equilibrium constant, Kc or Kp, the products on the top, the reactants on the bottom, the liquids and aqueous, the exponent is the coefficient. It's called the law of mass action, but it gives a constant number at a specific temperature for a specific reaction. So it's kind of review. And then what we did is we were given the equilibrium values, and we used that K expression, and we just plugged in the numbers. And then we related Kc to Kp. And this again, I think it's a 15-minute lesson that I had posted for Friday, and it is still there. But I'm not going to work these again, because I did work them on that lesson. But I will give you the answers. So here on this sheet, and when we do the test, if I'm right, if we get to the 25th of March, and that is the day of our test, this equation I'll write on the board. Okay, I don't expect you to memorize it. It's not on the formula sheet. I don't think it's going to be on the AP test. But it will be on our test. And a matter of fact, if you look, and for those that are at home, I'll give you guys the quiz tomorrow. But for those that are here and that they just grabbed the quiz, you might want to note number 2. You're given Kc, solve for Kp. So again, this will come up. It's not a huge point, but it will be on the test. And it's on the quiz. But this one, here's the answers for this problem. So the Kc is 6.44 times 10 to the 5th. And one thing I don't think I made enough of a point of is that K is one of the rare numbers that we have that does not have a unit. It's one of the rare things that does not have a unit to it at all. I think if you guys go the science route or engineering or medicine route in college, I think, and I can't even remember now, maybe your junior year, K will have a unit. But for us, K doesn't, okay? So again, you guys can go through, and again, I've worked that problem online. And then this one, again, I did this one as well, and I'm not going to spend time now, but it would be worth doing things. So here, the pressure of the Cl2, so this is going to have a unit, because this is pressure, and the unit here, typically what we're doing units of pressure in is ATMs. So that was the answer to that one. Okay, and then this problem here, we're trying to find the Kc and the Kp. The Kp here is 0.236. Again, no units. And the Kc is
down a bit.
Oops. Okay. Thank you, Laura. Is that better?
Yeah.
0.0026. I'm recording this. Did I hit the record button?
Yeah.
Okay, that's review. You want to go over that. And again, that is going to be, again, not a huge thing, but it is on the quiz. It is going to be on our test. I don't think it's going to be on the AP test, but I wanted just to go over that and make sure. And to me, the thing that's tricky about that, that equation is this part. So the KP equals KC, but this is what's in parentheses. And then the delta N, remember, is the moles of the product minus the moles of the gaseous product, just the gas, minus the moles of the gaseous reactant. So that, again, I will write that on the board. Okay, all that's reviewed. Now I'm going into stuff that I did not get to where we left off. Here's another way that delta H is different from K. For me, and again, now we're getting, I think that today is March 8th. I think the date of our AP test is May 7th. So we're getting, we still have some good time to go. But we are getting a little bit more in the ballpark closer to the AP test. Okay, so what this is showing, just going back to this totaling of reactions, which we've now done a number of times. So for those of you guys that are at home, what I'm pointing out here is if you look in these two reactions, so what this says, multiple equilibria. Often a product of one reaction then becomes a reactant in a second reaction. That's an intermediate. Remember, we talked about that when we were talking about a catalyst intermediate at the end of chapter 12. Well, that's what happens here. In reaction 1, the H2CO3 makes H plus HCO3 bicarbonate ion. Well, in the second reaction, that HCO3, the bicarbonate ion, reacts, which means because I have HCO3 on the right in the first reaction and on the left, the second reaction, I can cancel that out, which gives me the overall reaction. But for K, different than what we did with delta H. With delta H, what we did was we just totaled everything up. We added it up. With K, we multiply. And so when I'm totaling reactions for K, I'm going to total those up. So if I do that here, what I get, so if I take 4.2 times 10 to the negative 7 times 4.8, bless you, times 10 to the negative 11. What I get for K here is 2 times 10 to the negative 17. Okay, so point here of this slide, when you're taking a series of reactions for K, to find the final K is you add, or you don't add them up. That's what you do with delta H. You multiply them all together. So quick review. What we said, how K is different than delta H. If for delta H, if we double the coefficients, we double the value for H. For K, we would square it. For delta H, if we flip the reaction, what we did is we changed the sign. What we do with K is we take the reciprocal. For if we do a multiple reactions, for delta H, we total. For K, we multiply. Okay, next thing is this thing called Q. This thing called the reaction quotient Q. Okay, so I'll give you guys a minute to copy this down. I'll explain what this is. This is, and again, we didn't, and some of you maybe were engaged last spring when we were going through this, but if this is like Le Chatelier with numbers, is what this is. And I'll explain that. Okay, so some of you are still copying this down, but if you remember, and you may have forgotten, but if you look back in your notes, at the beginning of the chapter, we talked about the graphs looking like this, and we made the point that when the graphs flattened out, that was equilibrium. And that's what the systems want to get to, is equilibrium. Well, what we're at now with this reaction quotient Q is we're here. We are before equilibrium. Okay, so the question we got here, whenever you see this, is this at equilibrium? Or if it asks this, which direction will the reaction proceed? Which is usually the question that will be asked. That means it's a Q problem. Now, Q problems you're going to do just like K. And for those of you that have the quiz, if you look on number 7, okay, it says, okay, at 448 degrees, we're given the reaction, we're given the value for K. In which direction will the reaction proceed? This is number 7 on the quiz, is a Q problem. Okay, now this is what you do. So, and what we're going to get to after we're done, especially today and tomorrow, we're going to do a lot of calculations. Today would be a really good day to have your calculators out. Is we're going to get into Le Chatelier, and Le Chatelier's principle is going to be no numbers. But what it says is if you have a system at equilibrium, everything's fine, and a change happens to the system, how will the system respond to the change? And basically, will it go right or left or no change? Well, we're going to do that without numbers. Okay, well, what we're going to do here is with numbers. It's like a Le Chatelier with numbers. So we do Q just like we do K. So the way I'm going to write this out is K just like I would Q. In terms of writing it out, it's going to be the same. So I'm going to have HI squared over H2 times I2. So I'm doing the same thing. In terms of, I'm saying the way that I wrote out K is the way I'm going to write out Q. Now, one point to make. In first year chem, every time the volume is 1 liter. Well, almost all the time in AP Chem, the volume is 1 liter. Because see, the brackets mean moles per liter. It means the concentration. It means the molarity. That's what the brackets mean. And see, if just like in this problem, if the volume is 1 liter, then the moles equals the molarity. So that's the case in this problem. So if I just plug in the numbers in, so I've got 1.98 squared, so I just plugged in HI, over 0.243 times 0.146. Now if this had not been 1 liter, I would have had to plug in, say it had been 2 liters. I would have had to do 1.98 divided by 2. 2.243, every one of them divided by 2 to get the units right. Now, I'll try and point that out when we see it. It doesn't come up a lot, but in AP chemistry, we're in the fire swamp. And so once in a while, those big rat creatures come up, and that could happen here. So if I go and do that on your calculator, so go 1.98 squared, enter, divided by 0.243, enter, divided by 0.146. What I get is 111. Did anybody else get that here at home?
Yep.
111, okay. Now we've done that. So again, Q is here before we got to equilibrium, which means Q is greater because it says for this reaction that the K is 54.3. So the first question says, is this reaction at equilibrium? The answer is no. It's not at equilibrium. The only way it would be at equilibrium is if the Q equaled K. If Q equals K, it's at equilibrium, but it's not. So is this reaction at equilibrium? No. Okay, now in which direction will this proceed? And I'm going to put up here in a second kind of the explanations, but this is the simple way. This works for me. But if I do a number line, and I've got K right here, K is 54.3. Can you see that, Mark?
Yeah.
Okay. It's good?
Yeah.
And then Q is 111. The way this works to predict which direction will this proceed is to put K and Q on a number line. And Q will always move towards K. I'll say that again. Q will always move towards K. K is the pillar. K is the foundation. Q will always move towards K. So in this case, this is going to move to the left. This reaction is going to go to the left. Now, to me, that's the easy way to do it. And with all the difficult stuff we do in this class, to have a simple way to do it is nice. But if you think about it, and you guys think way better than me, but I need to get Q smaller, which means I need the number down here in the denominator to get smaller. To get larger, and I need the number up here in the numerator to get smaller. Well, if it goes left, that's what's going to happen, is the reactants are going to get larger and the products are going to get smaller. So when you're asked, like on number 7 on the quiz, which direction will it go, and you're given the values, plug it all in, and then Q will move towards K. We're going to do another one at the end of class. Now here is if this makes more sense for you, fine. But to me, put Q and K in a number line, and then Q will always move towards K. But if this makes more sense, then do this. Q is equal to K, is at equilibrium. And just like the second one we just did here, if Q is greater than K, then Q is going to move to the left. The products will change to the reactants. The reaction will proceed left, and then the opposite if Q is smaller. So this reaction quotient is just doing K, but it's just seeing how this Q compares to K.
Just have to pass this out urgent.
Okay,
It's for later.
I will get this to you. Okay, so now we're really going to go into the fire swamp for kind of that was a terrible. Okay, so here we go. I'll let you guys read this one. I kind of want to come back and look at some of the problems on the quiz, just kind of see the different kind of problems that were given. This is the same reaction we just did, just different numbers. Okay, so here's my reaction. So I've got H2 plus I2 makes 2HI. And we're told K, just like it says here, 54.3. So I don't know, to me, in doing chemistry problems, it's kind of like my daughter, she was an English major, so probably writing or talking, really a good thing for majors like that to solve problems. To me, writing is always a big deal for me just to kind of make sense of everything that is going on here. So if I read this, so here's the reaction. It says a mixture of 0.5 moles of H2 and 0.5 moles of I2 are placed in 1 liter. 1 liter, so that's nice. At 430 degrees Celsius, calculate the concentration of each species when equilibrium is established. So so kind of the quick review of what we've done so far. We talked about what equilibrium was. Then we talked about this equilibrium expression, products over reactants. Then we were given numbers, which were just the equilibrium concentrations. We plugged them in and we calculated. Now we're getting where we're two different kind of sets. We have where we initially mixed it and at equilibrium. We've got to go back to the dreaded ice table. So when we have a problem that says, okay, we start with this and at equilibrium, we've got to do an ice table. Now, if a problem just says we're at equilibrium, we plug in the numbers. Now, the value for K, or I should say, the equation for K is going to be HI squared over H2 times I2. Okay, so we talked about that. That's kind of going back to the basics. Okay, we products on top, the coefficient became the exponent, reactants on the bottom. But again, if you read this, a mixture of 0.5 moles of H2, 0.5 moles of I2 are placed in a 1 liter container. Calculate the concentration of everything when equilibrium is established. So we have two different sets. Now, what this means again is initial. To me, this is what you start with, the ice. C is the change, and E is really equilibrium, which is really what you end with. It's kind of start, change, finish. That's how it works. And the way almost every problem works is what we start with here on the left side is given. We are given the initial amounts. On the right side, almost every single time, we start with 0. We haven't made anything. So initially, we haven't made anything. Now, here, we do not know about anything about equilibrium. The actual question is it says calculate the concentration of H2, I2, and HI. They've given me the value for K. They said that this was 54.3. It's to figure out these concentrations. Well, I'm just going to say, now on the left side, here's some basics of the ice table. On the left side, you have an initial amount in the I row. On the right side, on the product side, you haven't made any 0. In the C, and the C is probably the key part to this, of these ice tables. The C part, on the left side, you subtract because you're making, or you're using these, you're consuming these. And since this is 1-to-1, if this was X, this would be X too. So I have 0.500 minus X, 0.500 minus X. Okay, now on the right side, in the C column, we're gonna be producing. We're going to be making the product, so its amount's going to go up. But this is where we want to look at the mole ratio. If this was X, and this was X, and it was 1-to-1, and this is 2, what should go here? It's 1-to-1, and this was X to X. It's kind of a tougher question. It's 2X, right? Good, Carson. It would be 2X. And the reason it's 2 is because 1 for X, 1 for X. Well, here we make twice as much, so it's 2X. So I get 2X. Okay, so now I'm going to plug these things in. So I'm going to put 2X here. So I get 2X squared. Okay, and then I'm going to put this here and this here. So I get 0.500 minus X. And we're down in the fire swamp now. Those fire things are coming up, and those big rats are walking around. Now it's an algebra problem. So I can combine these two. 54.3 equals 2X squared over 0.500 minus X squared. Right?
Are we about to get to the quicksand?
We are about to get to the quicksand is going to come tomorrow.
Okay.
The quicksand is tomorrow. Okay, so mathematically now, what should I do? I want to get rid of the squares. I don't like the squares. I'm going to take the square root. So do the square root. So if I do the square root of 54.3, gives me, so I'll just write up here, 7.37. So that was the square root of 54.3. Now is equal to 2X over 0.500 minus x. Now it's a little bit more manageable problem. Okay, see if you can solve for x. Let's do some algebra here. See if you can solve for x. Cross multiplied. Go down a little bit, or maybe tilt it a little bit this way. Is that better, Laura? Good. Thank you again. Gives me 0.393. Good. Okay, so again, a little bit of some math there. But the question was to calculate the concentration. So for H2, what we said the concentration was 0.500 minus x. For the I2, it was 0.500 minus x. And for the HI, it was 2x. Well, now we know x. So I'm going to put that, so the value for x is 0.393. So I'm going to put that here. So I have 0.500 minus 0.393. So I found x, I plugged that in. So that gives me 0.107. And that is molarity. This time we're trying to find the concentration at equilibrium. I2 will be the same thing. So it'll be 0.500 minus 0.393. Okay, and then for HI, it'll be 2 times 0.393. So that'll be 0.786. That's a good problem. The quicksand's tomorrow, but the big rats are running around, and those fire pits are flaring up. I told you guys since we started class, it's a good idea to go back and do problems we did in class. That would be a good one to do sometime tonight. Okay, let me just put up next slide. Let's just look at this, and then this will lead us into the quicksand, which we'll get into tomorrow. Let's see if you guys can figure this one out. This is still the same reaction. So I'm going to erase the board. So again, I have been filming this, so if you want to go back and watch that again, you can. question here is, which direction will this proceed? This is a Q problem. And ask, is this at equilibrium, or which direction will this proceed? This is a Q problem, which we do just like a K problem. I get 19.45. That's the value for Q. All right. So again, which direction is this going to go? So on a number line, I have K right here, which is 54.3. Oops, this is K. And here's Q, which is 19.45. Remember, Q always moves towards K. K is the pillar. K doesn't move. Q always moves towards K, which means this is going to go to the right. This is going to go to the right. And then this will lead us, like Lori correctly says, into the fire swamp tomorrow with that question. And I'll deal with that one. We'll deal with that one tomorrow. I wouldn't worry about that one. So, okay, I'm going to stop there. Those of you that are in class, I need the penny sulfur lab in one pile, the quiz in the other pile. If you have questions, you can ask. Those of you that are at home, I am done today. So those of you at home, I'm done. If you have questions, you can stay on. If not, I will see you guys tomorrow.
Thank you.